Hello everyone and welcome to this procedure video for the Room 2003 Science Physical Science class. This video covers balancing chemical equations. As we get started, let's talk about presentation layout. Here is a table of contents, and the first thing we're going to cover is connection to the previous lesson on slide 3. And then I have a website that I'm recommending for you to go to and explore and play with on slide 4. We're going to review the law of conservation of matter and what that means in regards to balancing chemical equations. Then we're going to get into a 6-step procedure for balancing equations with an example problem to follow and practice problems after that. There are 5 practice problems for you to work on, and they are due May 4th. And as we have been doing, please email pictures of your final balanced equations. In the previous lesson, in chemical reactions and equations, we learned about these things: the connection between chemical equations, chemical change, and chemical reaction, how to read chemical equations, including things like what are the reactants, what are the products, what are subscripts, what are coefficients, those sorts of things, what the plus symbol and the arrow symbol mean. We learned how chemical equations must be balanced to satisfy the law of conservation of matter. This is true to satisfy this law, but it is also true if we're going to use chemical reactions to our benefit. We need to balance the chemical equations. An example of this is an internal combustion engine, a car. The amount of fuel and air is mixed according to balanced chemical equations to be most efficient and to help the car to run the best that it can. We learned how balancing may be accomplished using coefficients, and at the same time we are not allowed to change subscripts to balance equations, because when we do that we change the substances, and the law of conservation of matter does not permit this to happen. If we have a chemical reaction with a certain set of things that go in and a certain set of things that come out, we cannot change those, and when we change subscripts, that's what we do. So here is how we connect to the previous lesson in chemical reactions and equations, and we're going to build on this, what we learned about in that lesson. So I have a website recommended for you. I thought about making this a part of the lesson, but not knowing how well your internet connectivity will hold up at home, I decided just to recommend it to you. And it is a great simulation for visualizing the balancing process. So what you want to do is Google that phrase in parentheses, PHET, balancing chemical equations, and this website will be the first hit that you get. And when you click on the link, you're going to see a screen that looks like this. Click the introduction icon and just start playing. When you first get into it, it won't be obvious what to do, but there will be arrow buttons, and just start clicking drop down boxes, see how it changes, and just start exploring and playing with it. And as you do it, you will see visualizations about chemical equations that you are changing, and you'll figure it out. So just get in there and play with that. It's a great visualization tool. You won't break it, and it'll help you just have some pictures to go with this idea of balancing chemical equations. And then after the introduction, if you like, go to the game icon at the bottom of the screen, choose the level of difficulty. I recommend level 1 starting out, but you can go to level 2, level 3 to make them a little bit harder. And again, just explore and play with balancing equations, and great visual tool. And in fact, the process that we're going to see here in this slide presentation is modeled after that tool, after the game version of that tool. All right, so before we get started, with the actual process, let's review what the law of conservation of matter says and what it means. So what it says is matter cannot be created or destroyed, which sounds all well and good on its own, but when we start balancing chemical equations, we have to understand what that means. And what it means is, for one thing, the number of atoms of each element that go into the reaction must equal the number of atoms of each element that come out of the reaction. So if I have 6 oxygen on the left-hand side, I must have 6 oxygen atoms come out on the right-hand side. And remember, the arrow symbol is the divider between goes in and comes out. It also means we can only work with the substance particles represented in the equation. Now remember, a substance can be an element or a compound. It can be a molecule or a single atom. But whatever is represented in the chemical equation, those are the only substances we can work with. We cannot add or take away from those substances. So we cannot add, if a single oxygen atom is not in the reactants, we can't add it just for the sake of balancing. And as we mentioned before, we may not change the subscripts of any reactants or products. To do so changes their identity, and again, this is not allowed by the law of conservation of matter. If water was not in there to begin with, we cannot change the subscript and create water when it wasn't there. So balancing chemical equations, I approach this in a 6-step process, and there are a couple check steps that you may consider, a couple checkpoints that you may consider steps. I really don't count those as steps, but well, a couple questions built into the process, and you'll see those. I don't count the questions as steps, but we will see them in this flow chart. So the first step, step 1, is write the equation. This is perhaps the easiest part. Step 2 is draw particle models. It is important to make balancing chemical equations when you're getting started, to make it as visual as possible. This will really help you. So step 2 is key, to draw these particle models. Step 3, check for balance. What that means is, do the number of atoms of each element on the reactant side equal the number of elements of each atom on the product side? If they do, so we're going to check for balance. Is it balanced? If yes, then you're done. It's already balanced. You don't need to do anything. However, as you can probably guess, I'm going to give you equations which are not balanced. At that point, you are going to add particles where more atoms are needed. Now this next to step number 2, this is key. We have to add whole particles, the particles that are in the equation. We cannot add part of a particle. We have to add whole particles, and this is why number 2 is so important. Number 2 will help you visualize the particles, will help you see the particles, and make sure that when you add them, you add whole particles and not just subparts of particles. So we're going to add particles where more atoms are needed, and then we're going to recheck for balance. And if we're not balanced, we're going to go back to number 4. So 4 and 5, we get into a loop. This is where the balancing happens. And we keep, at step 5, if it's not balanced, we add particles where more atoms are needed. And we keep doing that until we are balanced. And if we're balanced, then we count particles and rewrite the equation. Count particles, that little phrase is where we get our coefficient. So count particles means we get our coefficient and rewrite the equation with those coefficients. Once we have accomplished that, then we are done. So take a moment and pause the video and look this slide over again. And if you want to, copy this slide down, and or refer back to it as much as you need to as you work through the practice, as you work through the homework problems. Let's get into an example then. Step number 1, write the equation. So obviously I'll give you the equation. You need to write that and add some space. The spaces between the element or substance symbols, Fe plus O2, those spaces allow for you to draw for step 2 to draw the particle models. So leave yourself plenty of space, and you can always take the space, you will take the space out when you write the final equation, but as you're balancing, leave yourself plenty of space. So number 2, we're going to draw particle models. Well, Fe, iron, is just a single atom in the particle. So I put the symbol within a particle outline. O2, however, is 2 oxygen atoms within the particle. So I split that apart so that I can count that up and compare that from side to side, and the O2 particle looks like that. And then Fe2O3, I'm going to have 2 iron and 3 oxygen atoms in that particle. So step 2 will help you visualize when we need to balance, we have to add whole particles. And this step helps you visualize that. So if I need more iron on the left side, I can add that 1 iron at a time. If I need more iron on the right side, I have to add a whole entire Fe2O3 iron oxide particle at one time. So we're going to check for balance. Well, what does that look like? On the reactant side, the left side, I have 1 iron and 2 oxygen. On the product side, I have 2 iron and 3 oxygen. I am not balanced here at the iron, and I'm not balanced here. The reason I put the X's on the left side is I put them where I have fewer atoms. So on the reactant side, I only have 1 compared to the product side where I have 2. So when I start balancing, I'm going to start balancing on the side with the lower amount of atoms. So I'm not balanced, and I need to start on the reactant side with both particles. So I'm going to add particles where more atoms are needed. So what's that look like? Well, I'm low on the iron on the reactant side, so I'm going to add an iron. I'm low on the oxygen on the reactant side, so I'm going to add an O2 particle. I can't just add 1 oxygen because I don't have a single oxygen particle on the reactant side. And then I'm going to recheck for balance. Now on the reactant side and the product side, I'm good on the iron. I have 2 and 2. However, on the oxygen, now I have 1 more oxygen on the reactant side than I have on the product side. So I'm out of balance. I'm close, but I'm not there yet. And where I need to balance is on the product side, where I need to add to. So take a moment, look at this slide, and then we'll go on to the next step. Remember, at step 5, we recheck for balance. If we're not balanced, we go back into step 4. All right, so at the top of this slide, we see the same check table that we had on the previous slide. I'm low on the reactant side with oxygen. Unfortunately, according to the law of conservation of matter, I have to add an entire iron oxide particle. So I can't just add 1 oxygen. I have to add a particle containing 2 irons and 3 oxygens. Let's recheck for balance. Now I am out again on both the iron and the oxygen. As you balance, it's common for this to happen. Typically, you will have to go through more than 1 cycle or iteration to get it to balance. And in this case, it looks bad because we went out on both iron and oxygen on the reactant side, but we're really quite close. So same check table at the top of the slide. We have to add particles. I'm low on iron, but in this case, I see that the difference is 2, and I can add single irons at a time. So I'm going to go ahead and add 2 iron particles, and I'm low on oxygen by 2. So there is my O2 particle. I'm going to recheck for balance, and lo and behold. So if you look at the 2 tables, the table at the top, it looked kind of bad because we went out of balance. It didn't look like we were going to be able to make it happen. But in this last iteration, we were able to bring the iron into balance and the oxygen into balance. That brings us to our final step. We are balanced. Now we're going to count particles and rewrite the equation. Remember, count particles means that's our coefficient. So starting on the left side, I have 1, 2, 3, 4 iron particles. That's going to look like this. 4 is the coefficient. Fe, capital F, lowercase e is the symbol for the particle. Plus 1, 2, 3 O2 particles. We don't make that 6O. Our particle is O2, and we have 3 of those. Yields 1, 2, 2 iron oxide particles. So there is the final equation. And when you write the final equation, feel free to take the spaces out. I left them spaced out so visually they lined up with the drawings. But feel free to take the spaces out and condense that format just a little bit. That takes us through how to balance chemical equations in 6 steps. It may seem like a little bit of a pain to draw the particle models, but as you're getting started with this, it is, to me, indispensable to do that. It will really help if you draw the particle models. Iron oxide is a little bit of a pain because there are 5 atoms in it, but it just helps you to visualize the process. And then once you get some practice, you may be able to not draw and kind of skip that step. But as you're learning, I definitely recommend you draw the particles models and make it more visual for yourself. So again, final equation. 4 iron particles, 4 Fe plus 3 O2 particles, 3 O2 yields 2 iron oxide particles, 2 Fe2O3s. All right, here are your 5 practice problems. Jump in, follow that procedure, follow those 6 steps, draw the particle models, and you will find that by the time you get to number 5, it is making quite a bit of sense. Now, number 5 is a little more difficult. There's a few more iterations, but just stick with the process. Always add particles where you have a lower number of atoms. And you'll get to a certain point, you'll feel like you're never going to finish, and then all at once it balances. So just stay with it. All right, that brings us to the end of this homework video, balancing chemical equations for my physical science classes. That is the physical science classes that meet in room 2003 science. Please do not hesitate to email or call or join the Google Meet. And as always, be safe and be well.